We begin with the only place we've ever truly called home, Earth, a blue and green sphere suspended in the darkness, wrapped in a thin veil of atmosphere, teeming with life. From space, it looks peaceful, fragile, a floating island in a vast, silent ocean. But Earth is not the center of everything. It's just the starting point. And to understand the scale of the universe, we must first leave it behind. Our journey begins with a single step outward, to the moon. It's the closest object in space that orbits our planet, familiar in the night sky, yet distant in ways that defy intuition. The moon orbits Earth at an average distance of 384,400 kilometers. That number is hard to grasp. So let's break it down. Imagine lining up Earths side by side. You'd need about 30 of them to span the gap between Earth and the moon. That's how far it really is. If you could drive a car straight to the moon at highway speed, say 100 kilometers per hour, it would take you roughly 160 days of nonstop driving. No breaks, no sleep, just a straight line through the vacuum of space. Even light, the fastest thing in the universe, takes time to travel that distance. From the moon to Earth, light takes about 1.3 seconds. That delay is tiny, but it's real, and it becomes more noticeable the farther we go. The moon itself is a quiet, airless world. It has no atmosphere, no wind, no rain. Its surface is covered in fine dust and craters from ancient impacts. It's a place frozen in time. When astronauts first landed there in 1969, they left footprints. Those prints are still there today, untouched by weather or erosion. The moon preserves history in a way Earth cannot. Its gravity is just 1/6 of Earth's. That means you'd weigh much less there. You could jump higher, move more slowly. It's familiar, but strange. A world that feels both close and alien. Standing on the moon, Earth looks small, a glowing marble hanging in the blackness. From that vantage point, you begin to understand scale. You begin to feel distance. The moon has phases, waxing and waning, because of its orbit around Earth. It reflects sunlight, and its appearance changes depending on its position. But it's always there, locked in a gravitational dance with our planet. It's tidally locked, meaning the same side always faces Earth. We never see the far side from the ground. That hidden hemisphere remained a mystery until spacecraft revealed its rugged terrain. The moon's influence on Earth is profound. It stabilizes our planet's axial tilt, which helps regulate climate. It causes tides pulling on Earth's oceans with its gravity. It's not just a companion, it's a force. And yet, it's just the first step. The moon is the closest object in space, but it's still incredibly far. And beyond it, the distances grow exponentially. Before we move on, let's pause. Let's look back at Earth from the moon. From that distance, Earth is a sphere of color and motion. You can see clouds swirling, continents drifting, oceans shimmering. It's alive, it's dynamic, and it's small. Everything we've ever known, every person, every story, every civilization exists on that tiny globe. From the moon, it's clear. We are part of something much larger. The moon reminds us of our reach. We've been there. We've touched another world, but it also reminds us of our limits. We've only just begun. In terms of scale, the moon is a mere stepping stone. Beyond it lies the sun, the planets, the stars, and the edge of the observable universe. Each step outward multiplies the distance. Each milestone reveals more of the vastness. But the moon is important. It's the threshold, the place where humanity first crossed into space, the place where we proved we could leave the Earth behind. It's also a place we may return to. Future missions aim to build bases, study its geology, and use it as a launch point for deeper exploration. The moon could become a gateway to Mars and beyond. Its surface holds clues about the early solar system. Without atmosphere or tectonic activity, it preserves ancient records. Studying it helps us understand how planets form and evolve. The moon also offers a unique vantage point. Without atmospheric distortion, telescopes placed there could observe the universe with unprecedented clarity. It's a quiet platform for science. And culturally, the moon has always been a symbol. It appears in myths, poems, calendars. It marks time, inspires wonder, and connects generations. It's more than rock and dust. It's part of our story. The moon has no magnetic field. Its surface is bombarded by solar radiation and micrometeorites. It's harsh, but it's accessible. It's the only celestial body humans have walked on. The Apollo missions taught us how to navigate space, how to land, how to survive. They laid the groundwork for everything that followed. The moon was our training ground. Today, robotic missions continue to study the moon. Orbiters map its surface, landers analyze its soil, rovers explore its terrain. Each mission adds to our understanding. The moon's south pole is of particular interest. It contains permanently shadowed regions that may hold water ice. That resource could support future human missions. International efforts are underway. NASA's Artemis program, China's Chang'e missions, and other agencies aim to return humans to the moon. It's a global endeavor. The moon may also serve as a launch site. Its low gravity makes it easier to send spacecraft deeper into space. It could become a hub for interplanetary travel, but for now, it remains a quiet witness, a place we visited, studied, and left behind, a reminder of what's possible. As we prepare to leave the moon behind, we carry its lessons with us, the lesson of distance, the lesson of perspective, the lesson of possibility. We now turn our gaze toward the sun. It's the dominant force in our solar system, a star that gives us light, warmth, and gravity, and it's much farther than the moon. But before we go, let's take one last look. The moon, silent and gray, floating in the black. Earth, vibrant and blue, spinning in the distance. Between them, a vast emptiness. And yet, we crossed it. This was the first step, the first leap into the unknown. And now, we continue. Let's zoom out. We now leave the moon behind. The closest object in space, the first step outward. It taught us about distance, perspective, and possibility. But the journey has only begun. Our next destination is the sun, the central star of our solar system, the source of light, heat and gravity that holds everything together. It dominates our cosmic neighborhood. The sun is far larger than anything we've seen so far. Its mass accounts for more than 99.8% of all the matter in the solar system. Everything else, planets, moons, asteroids, makes up less than 1%. The distance from Earth to the Sun is about 149.6 million kilometers. This is known as 1 astronomical unit, or AU. It's a standard measure used to describe distances within our solar system. To grasp this distance, imagine driving to the sun at highway speed, 100 kilometers per hour. It would take you over 170 years of nonstop driving. No breaks, no sleep, just a straight line through space. Light from the sun takes about 8 minutes and 20 seconds to reach Earth. That means when you look at the sun, you're seeing it as it was more than 8 minutes ago. Even light needs time to cross space. The sun is a massive ball of hydrogen and helium undergoing nuclear fusion. In its core, hydrogen atoms are fused into helium, releasing energy. That energy travels outward and eventually radiates into space. The surface temperature of the sun is about 5,500 degrees Celsius, but its core reaches over 15 million degrees. It's a furnace of unimaginable power. The sun's diameter is about 1.39 million kilometers. You could line up 109 Earths across its face. Its volume could fit over 1.3 million Earths inside. Despite its size, the sun is classified as a G-type main sequence star. It's not unusually large or small. It's average as stars go. But to us, it's everything. The sun's gravity holds the planets in orbit. It shapes the paths of comets and asteroids. It influences space weather and solar wind. It's the anchor of our system. Solar wind is a stream of charged particles released from the sun's upper atmosphere. It travels through space and interacts with planetary magnetic fields. On Earth, it causes auroras near the poles. The sun has cycles. Every 11 years, its magnetic activity peaks. Sunspots appear, solar flares erupt. Coronal mass ejections send waves of energy into space. These events can affect satellites and power grids. The sun's light powers photosynthesis. It drives weather. It warms oceans. It's the foundation of life on Earth. Without it, our planet would be frozen and lifeless. And yet, we rarely think about its distance. It feels close because we see it every day. But it's far, very far. And that distance is just the beginning.
Between Earth and the Sun lies a region filled with activity. There are solar observatories, satellites, and probes. One of the most notable is the Parker Solar Probe. Launched by NASA, the Parker Solar Probe is designed to study the Sun's outer atmosphere. It travels closer to the Sun than any spacecraft before it. It endures extreme heat and radiation to gather data. Its mission helps us understand solar wind, magnetic fields, and the structure of corona. It's a step toward predicting solar storms and protecting technology on Earth. The space between Earth and the Sun also includes the orbit of Mercury. Mercury is the closest planet to the Sun. It orbits at an average distance of 58 million kilometers. Mercury is a rocky world with no atmosphere. Its surface is scorched by solar radiation. Temperatures swing from extremely hot to freezing cold. It's a planet of extremes. Despite its proximity to the Sun, Mercury is not the hottest planet. That title belongs to Venus, which has a thick atmosphere that traps heat. But Mercury is still harsh. The sun's influence extends far beyond Mercury. It reaches all the way to the edge of the solar system. Its gravity holds distant objects in orbit. Its light travels billions of kilometers. The inner solar system includes Mercury, Venus, Earth, and Mars. These are the terrestrial planets, rocky, compact, and relatively close to the sun. Venus orbits at about 108 million kilometers from the sun. It's similar in size to Earth, but has a dense atmosphere of carbon dioxide. Surface temperatures exceed 460 degrees Celsius. Venus rotates slowly and in the opposite direction of most planets. A day on Venus is longer than its year. Its thick clouds reflect sunlight, making it the brightest planet in our sky. Mars orbits at about 228 million kilometers from the sun. It's colder and smaller than Earth. Its thin atmosphere cannot retain heat. Surface temperatures vary widely. Mars has seasons, polar ice caps, and evidence of ancient rivers. It's a focus of exploration. Rovers study its soil. Orbiters map its terrain. Future missions aim to send humans. Between Mars and Jupiter lies the asteroid belt. It's a region filled with rocky debris. These objects are remnants from the early solar system. They never formed into a planet. The asteroid belt marks the boundary between the inner and outer solar system. Beyond it, the planets become larger and more distant. The scale begins to shift dramatically. But for now, we focus on the sun. It's the center, the source, the reason our solar system exists. The sun formed about 4.6 billion years ago from a cloud of gas and dust. Gravity pulled material together. Nuclear fusion ignited. A star was born. Around it, leftover material formed planets, moons, and asteroids. The solar system took shape. Earth emerged. Life began. The sun will continue shining for billions of years. Eventually, it will exhaust its hydrogen fuel. It will expand into a red giant, engulfing Mercury and Venus, possibly Earth. After that, it will shed its outer layers and become a white dwarf, a dense, cooling remnant. The solar system will change forever, but that's far in the future. For now, the sun remains stable. It continues to shine. It continues to hold everything in place. We've studied the sun for centuries. Ancient cultures worshipped it. Early astronomers tracked its motion. Modern science probes its secrets. Solar eclipses reveal its corona. Telescopes observe sunspots. Satellites monitor its activity. We've learned much, but mysteries remain. The sun's magnetic field is complex. Its cycles are not fully understood. Its influence on climate and technology is still being explored. And yet, it's familiar. It rises and sets. It marks time. It warms skin. It lights landscapes. It's part of daily life. But in space, it's a massive, distant object. A sphere of plasma. A nuclear engine. A gravitational anchor. From the moon, the sun looks brighter. There's no atmosphere to scatter light. Shadows are sharp. The sky is black. The sun dominates. From Mercury, the sun appears 3 times larger than from Earth. Its heat is intense. Its radiation is constant. It's overwhelming. From Earth, the sun is just the right distance. Not too close. Not too far. The Goldilocks zone, where liquid water can exist, where life can thrive. This balance is rare. Most planets are too hot or too cold. Earth's position is fortunate. It's a narrow window in a vast range of possibilities. The sun's light takes 8 minutes to reach us, but it took thousands of years to travel from its core to the surface. Energy moves slowly through dense layers before escaping. That energy powers everything. It drives ecosystems. It fuels growth. It shapes climate. It's the foundation of biology. And it's constant. The sun has shone for billions of years. It will shine for billions more. It's a stable presence in an unstable universe. As we prepare to move beyond the sun, we acknowledge its role. It's the center of our system, the source of our existence, the beginning of our journey. Beyond the sun lie the outer planets, gas giants, ice worlds, distant moons, and eventually the edge of the solar system. But the sun remains the anchor, the reference point, the light in the darkness. Let's take one last look. The sun, massive and bright, floating in space. Earth, orbiting at a safe distance. The moon, trailing behind. Mercury, Venus, Mars, all caught in its pull. This is the inner solar system, a region shaped by gravity and light, a region we've begun to explore. And now we continue. Let's zoom out. We now move beyond the inner solar system, past the rocky planets, past the asteroid belt, into a region where scale begins to shift dramatically. The outer solar system is vast, cold, and filled with giants. Our journey begins with Jupiter. It's the largest planet in the solar system, a gas giant with no solid surface, composed mostly of hydrogen and helium. Its mass is more than twice that of all the other planets combined. Jupiter orbits the Sun at an average distance of 778 million kilometers. That's more than 5 times the distance between Earth and the sunlight. It takes about 43 minutes to travel from the Sun to Jupiter. Its diameter is about 143,000 kilometers. You could fit 11 Earths across its equator. Its volume could hold over 1,300 Earths. It's immense. Jupiter's atmosphere is turbulent. Bands of clouds swirl around the planet. Storms rage for centuries. The most famous is the Great Red Spot, a massive storm larger than Earth. Jupiter has a strong magnetic field. It's the most powerful of any planet. It traps charged particles and creates intense radiation belts. Its magnetosphere extends millions of kilometers into space. It also has a faint ring system, not as prominent as Saturn's, but present. Dust and debris orbit the planet, shaped by gravity and magnetic forces. Jupiter has dozens of moons. The 4 largest, Io, Europa, Ganymede, and Callisto, are known as the Galilean moons. Each is unique. Each could be a world of its own. Io is volcanic. Its surface is constantly reshaped by eruptions. Europa has an icy crust and may harbor a subsurface ocean. Ganymede is the largest moon in the solar system. Callisto is heavily cratered and ancient. These moons are targets for exploration. Europa, in particular, may have conditions suitable for life. Missions are planned to study its ocean and ice. Beyond Jupiter lies Saturn, another gas giant known for its spectacular rings. Saturn orbits the Sun at about 1.43 billion kilometers. Light takes about 80 minutes to reach it. Saturn's diameter is about 120,000 kilometers. It's less dense than water. If you could find a large enough ocean, Saturn would float. Its rings are made of ice and rock. They span hundreds of thousands of kilometers, but are only about 10 meters thick. They're delicate and dynamic. Saturn has a complex atmosphere. Bands of clouds, storms, and winds shape its appearance. It has a hexagonal storm at its north pole, a geometric feature unlike anything else. Saturn also has a strong magnetic field, not as intense as Jupiter's, but still significant. It influences its moons and rings. It has over 80 known moons. The most famous is Titan. Titan has a thick atmosphere, lakes of liquid methane, and a surface shaped by weather. It's one of the most Earth-like bodies in the solar system. Another moon, Enceladus, has geysers that shoot water vapor into space. These plumes suggest a subsurface ocean. Like Europa, Enceladus may harbor life. Saturn's moons are diverse. Rocky, icy, active, dormant. Each adds to our understanding of planetary systems. Beyond Saturn lies Uranus. It's an ice giant composed mostly of water, ammonia, and methane. It orbits the Sun at about 2.87 billion kilometers. Light takes nearly 160 minutes to reach it. Uranus is unique. It rotates on its side. Its axis is tilted by about 98 degrees. This causes extreme seasons and unusual weather patterns. Its diameter is about 51,000 kilometers. It has a faint ring system and a pale blue color due to methane in its atmosphere. Uranus has 27 known moons. Most are small and irregular. Some are named after characters from Shakespeare. They orbit in complex patterns. Its magnetic field is tilted and offset from its center. It's asymmetric and dynamic. It interacts with the solar wind in unpredictable ways. Uranus is cold. Its atmosphere reaches temperatures as low as minus 224 degrees Celsius. It emits little heat. Its internal activity is minimal. Despite its distance, Uranus has been studied by telescopes and spacecraft. Voyager 2 flew by in 1986. Future missions may explore it further. Beyond Uranus lies Neptune, the farthest known planet in the solar system. Another ice giant, similar in composition to Uranus but more active. Neptune orbits the Sun at about 4.5 billion kilometers. Light takes over 4 hours to reach it. It's distant, dark, and mysterious. Its diameter is about 49,000 kilometers. It has a deep blue color, also due to methane. Its atmosphere is dynamic, with the fastest winds in the solar system, up to 2,100 kilometers per hour. Neptune has a faint ring system and 14 known moons. The largest is Triton. Triton orbits in the opposite direction of Neptune's rotation. It's icy, geologically active, and may have a subsurface ocean. Triton is thought to be a captured object, possibly a former Kuiper Belt object. Its retrograde orbit supports this theory. Neptune emits more heat than it receives from the Sun. Its internal activity drives storms and weather. It's a planet of extremes. Voyager 2 visited Neptune in 1989. It remains the only spacecraft to do so. Images from that flyby revealed clouds, storms, and the structure of its rings. Beyond Neptune lies the Kuiper Belt, a region of icy bodies, dwarf planets, and debris. It extends from about 30 to 55 Australian dollars from the Sun. Pluto is part of the Kuiper Belt, once considered the ninth planet. It was reclassified as a dwarf planet in 2006. It orbits at an average distance of 5.9 billion kilometers. Pluto is small, about 2,377 kilometers in diameter. It has a thin atmosphere, icy mountains, and a heart-shaped plain called Tombaugh Regio. New Horizons flew by Pluto in 2015. It revealed a complex, active world, glaciers, haze layers, and possible cryovolcanoes. Pluto is more than a frozen rock. Pluto has 5 known moons. The largest, Charon, is about half its size. The two form a binary system, orbiting a common center of gravity. The Kuiper Belt contains many other objects. Eris, Haumea, Makemake, all dwarf planets. Thousands of smaller bodies orbit in this region. These objects are remnants from the early solar system. Studying them helps us understand formation, migration, and evolution. Beyond the Kuiper Belt lies the scattered disk, a region of distant, eccentric objects. It overlaps with the Kuiper Belt, but extends farther. And beyond that, possibly, lies the Oort cloud, a hypothetical sphere of icy bodies surrounding the solar system. It may extend up to 100,000 Australian dollars from the Sun. The Oort cloud is thought to be the source of long-period comets. It's distant, diffuse, and unconfirmed. No spacecraft has reached it. It remains theoretical. The outer solar system is vast. Distances are measured in astronomical units. Light takes hours, days, even years to travel. Communication with spacecraft is delayed. Voyager 1 and Voyager 2 are the farthest human-made objects. Launched in 1977, they explored the outer planets and now travel through interstellar space. Voyager 1 is over 24 billion kilometers from Earth. It takes more than 22 hours for signals to reach it. It carries a golden record, a message for any intelligent life it may encounter. The Voyagers revealed the structure of the outer solar system. They studied magnetic fields, atmospheres, moons, and rings. Their data transformed our understanding. Other missions include Galileo, Cassini, Juno, and New Horizons. Each explored different regions. Each added to the picture. The outer solar system is cold. Temperatures drop. Sunlight fades. Solar panels become ineffective. Missions rely on nuclear power. But it's rich in diversity. Gas giants, ice worlds, moons with oceans, rings of dust. It's a region of complexity and wonder. And it's still being explored. Telescopes study distant objects. Probes send back data. Plans for future missions are underway. The solar system is not just planets. It's a dynamic system of interactions. Gravity, magnetism, radiation, and motion shape everything, from Mars to Neptune, from Pluto to the Kuiper Belt. Each step outward reveals more. More distance, more scale, more mystery. We now prepare to leave the solar system, to move beyond the sun's influence, to enter interstellar space. But before we go, let's take one last look. The sun, far behind. The planets, orbiting in silence. The moon spinning. The belts drifting. The probes moving outward. This is our solar system, a region of light and shadow, a region we've begun to understand. And now we continue. Let's zoom out. We now leave the solar system behind, past the planets, past the Kuiper Belt, beyond the scattered disk. We enter interstellar space, the region between stars. It's vast, cold, and mostly empty. Our first destination is the nearest star system, Alpha Centauri. It's the closest group of stars beyond our sun, located about 4.37 light years away. It's still unimaginably distant. To understand this distance, let's convert light years into kilometers. 1 light year is about 9.46 trillion kilometers. So Alpha Centauri is roughly 41.3 trillion kilometers from Earth. If Voyager 1 were headed in that direction, which it's not, it would take over 75,000 years to reach Alpha Centauri at its current speed. That's longer than all of recorded human history. Even traveling at the speed of light, it would take more than 4 years to get there, and no current spacecraft can approach that speed. The gap between stars is enormous. Alpha Centauri is not a single star. It's a triple system. The two main stars, Alpha Centauri A and B, orbit each other. A third star, Proxima Centauri, is farther out and is the closest individual star to Earth. Proxima Centauri is about 4.24 light years away. It's a red dwarf, smaller and cooler than our sun. It's faint and hard to see without a telescope. Despite its small size, Proxima Centauri is active. It emits flares and radiation. It has at least 2 known planets. One of them, Proxima b, is in the habitable zone, the region where liquid water could exist. Proxima b is roughly Earth-sized. Its surface conditions are unknown. It may be rocky. It may have an atmosphere. It may be tidally locked, with one side always facing the star. The discovery of Proxima b sparked interest in interstellar travel. Could we send a probe? Could we study its atmosphere? Could life exist there? Projects like Breakthrough Starshot aim to send tiny spacecraft to Alpha Centauri. Using powerful lasers, these probes could reach 20% the speed of light. At that speed, the journey would take about 20 years. These probes would be small, gram-scale, and carry cameras and sensors. They'd fly by the system and send back data. It's ambitious. It's theoretical. But it's possible. Alpha Centauri A and B are sun-like stars. A is slightly larger and brighter. B is slightly smaller and cooler. They orbit each other every 80 years. Their combined light makes Alpha Centauri one of the brightest stars in the southern sky. It's visible to the naked eye from certain latitudes. The system has been studied for centuries. It's a target for exoplanet searches. It's a candidate for future missions. It's our nearest stellar neighbor. Beyond Alpha Centauri lie other nearby stars. Barnard's star is about 6 light years away. It's a red dwarf, older than the sun, and moving rapidly through space. Barnard's star is at least 1 planet, Barnard B. It's a super-Earth, possibly cold and rocky. Its orbit is wide. Its surface may be frozen. Lumen 16 is a binary brown dwarf system about 6.5 light years away. Brown dwarfs are objects too massive to be planets, but not massive enough to sustain fusion like stars. They emit little light. They're hard to detect, but they're common. Lumen 16 is one of the closest known systems. It's faint but nearby. Wolf 359 is another red dwarf, located about 7.8 light years away. It's small, dim, and active. It's often used in science fiction due to its proximity. Sirius, the brightest star in our night sky, is about 8.6 light years away. It's a binary system, Sirius A and Sirius B. A is a main sequence star. B is a white dwarf. Sirius A is twice as massive as the Sun. Sirius B is the remnant of a star that exhausted its fuel. The contrast between them is striking. Sirius is prominent in mythology and navigation. It's part of the constellation Canis Major. It's visible from most of Earth. Other nearby stars include Ross 154, Ross 248, and Epsilon Eridani. Most are red dwarfs. Most are faint, but they're close in cosmic terms. Epsilon Eridani is about 10.5 light-years away. It's similar to the Sun and has a known planet. It's a candidate for further study. Tau Ceti is about 12 light-years away. It's Sun-like and has multiple planet candidates. It's stable and quiet. It's often considered in discussions of habitability. The region within 15 light-years of Earth contains dozens of stars. Most are small. Most are red dwarfs. A few are Sun-like. A few are white dwarfs. This neighborhood is sparse. Stars are separated by trillions of kilometers. Space between them is mostly vacuum. Dust, gas, and particles drift slowly. Interstellar space is not empty. It contains the interstellar medium, a thin mix of hydrogen, helium, and cosmic rays. It's cold and diffuse. The density of the interstellar medium is low, about 1 atom per cubic centimeter. But over vast distances, it adds up. It shapes star formation and galactic structure. Cosmic rays are high-energy particles from distant sources. They travel through space and interact with matter. They pose challenges for spacecraft and astronauts. Magnetic fields also permeate interstellar space. They influence particle motion and radiation. They're weak but widespread. As we move farther from the Sun, its influence fades. The solar wind slows. The heliosphere ends. We enter the interstellar medium. Voyager 1 crossed the heliopause in 2012. Voyager 2 followed in 2018. They now travel through interstellar space, sending back data. They measure particle density, magnetic fields, and cosmic rays. They help us understand the boundary between solar and interstellar space. The region between stars is vast. Travel is slow. Communication is delayed. Missions must be autonomous. Power must be reliable. Future interstellar missions may use nuclear propulsion, solar sails, or laser-driven systems. Concepts are being studied. Challenges remain. Communication over light years requires powerful transmitters and long wait times. A message to Alpha Centauri would take over 4 years to arrive. Receiving data requires patience. Bandwidth is limited. Signal strength fades. Precision is essential. Navigation is complex. Stars move. Gravity shifts. Trajectories must be calculated with care. Corrections may be impossible once launched, but the rewards are immense. Studying nearby stars helps us understand stellar evolution, planetary systems, and the potential for life. Exoplanet research is growing. Thousands of planets have been discovered. Some are in habitable zones. Some are Earth-sized. Some may have atmospheres. Spectroscopy reveals composition. Transit methods show size and orbit. Radial velocity detects motion. Each technique adds to the picture. Alpha Centauri, Proxima Centauri, Barnard Star. These are the first steps, the first targets, the first destinations beyond our solar system. They're close in cosmic terms, but distant in human terms. Reaching them requires new technology, new thinking, and long-term commitment. Interstellar travel is not science fiction. It's a frontier, a challenge, a possibility. And it begins here with the nearest stars, with the systems we can see, with the light that reaches us. Let's take one last look. The solar system behind us, the Sun a distant point, the planets invisible, the probes drifting. Ahead, Alpha Centauri, a triple star system, a red dwarf, a possible Earth-like planet. Beyond that, more stars, more systems, more possibilities. This is our stellar neighborhood, sparse, quiet, and vast. We now shift our focus from nearby stars to the vast structure that contains them all, the Milky Way galaxy. It's our cosmic home, a sprawling system of stars, gas, dust, and dark matter. Everything we've explored so far exists within this single galaxy. The Milky Way is a barred spiral galaxy. It has a central bulge, spiral arms, and a surrounding halo. Its diameter is estimated to be about 100,000 light years. That means light takes 100,000 years to travel from one end to the other. It contains over 100 billion stars. Some estimates suggest there may be as many as 400 billion. These stars vary in size, age, and type. Some are massive and short-lived. Others are small and stable. Many have planets. Our solar system is located in one of the spiral arms, the Orion Arm. It's a minor arm situated between two larger ones, Sagittarius and Perseus. We're about 27,000 light years from the galactic center. From Earth, we can't see the full structure of the Milky Way. We're inside it, looking out, but we can observe its band across the night sky, a dense region of stars and dust. It's most visible from dark locations, far from city lights. The galactic center is a region of intense activity. It contains a supermassive black hole known as Sagittarius A star. This black hole has a mass of about 4 million times that of the Sun. It influences the motion of nearby stars and gas. Surrounding the center is a bulge, a dense, spherical region of older stars. Beyond that, the spiral arms extend outward, containing younger stars, nebulae, and star-forming regions. The arms are not solid structures. They're density waves, regions where stars and gas are temporarily compressed. As material moves through these waves, new stars are born. The galaxy also contains globular clusters, spherical groups of old stars that orbit the center. These clusters are found in the halo, which surrounds the disk of the galaxy. Dark matter plays a crucial role in the Milky Way structure. It doesn't emit light, but its gravitational effects are observable. It helps hold the galaxy together and influences its rotation. The rotation of the galaxy is complex. Stars near the center orbit faster than those farther out, but the outer regions rotate faster than expected, suggesting the presence of dark matter. The Milky Way is not static. It's dynamic. Stars move. Gas flows. New stars form. Old stars die. Supernovae explode, enriching the interstellar medium with heavy elements. Star formation occurs in nebulae, clouds of gas and dust. Gravity pulls material together. Nuclear fusion ignites. A star is born. Surrounding disks may form planets. The galaxy contains many types of stars. Massive blue stars live fast and die young. Red dwarfs burn slowly for billions of years. White dwarfs are remnants of dead stars. Neutron stars are dense cores left after supernovae. Pulsars are rotating neutron stars that emit beams of radiation. They pulse as they spin, creating regular signals. They help us study gravity, space-time, and stellar evolution. Black holes form when massive stars collapse. Some are stellar mass. Others, like Sagittarius A asterisk, are supermassive. They warp space and time. They influence their surroundings. The Milky Way also contains interstellar dust. It absorbs and scatters light, creating dark patches in the sky. It affects observations and plays a role in star formation. Gas in the galaxy exists in different phases: cold molecular clouds, warm ionized regions, and hot plasma. These phases interact and cycle through the galaxy. Supernovae inject energy into the interstellar medium. They create shock waves, trigger star formation, and distribute heavy elements. They're essential to galactic evolution. The Milky Way has satellite galaxies. The most prominent are the large and small Magellanic Clouds. They're irregular galaxies orbiting the Milky Way. They're visible from the southern hemisphere. Other satellites include dwarf spheroidal galaxies like Draco, Ursa Minor, and Sculptor. These galaxies are faint and contain few stars. They're dominated by dark matter. The Milky Way is part of a larger structure, the Local Group. It includes about 80 galaxies, most of them small. The largest are the Milky Way and Andromeda. Andromeda is a spiral galaxy located about 2.5 million light years away. It's similar in size to the Milky Way. It's approaching us and will eventually collide with our galaxy. This collision is expected in about 4 billion years. The galaxies will merge, forming a new elliptical galaxy. Stars will pass by each other. Gas will interact. New stars may form. The Milky Way's motion is influenced by gravity. It orbits the center of mass of the local group. It moves through space at hundreds of kilometers per second. Our solar system also orbits the galactic center. One orbit takes about 225 to 250 million years. This is known as a galactic year. Earth has completed about 20 orbits since it formed. The galaxy's history is long. It formed over 13 billion years ago. It grew by accreting gas and merging with smaller galaxies. Its structure evolved over time. Evidence of past mergers exists. Streams of stars trace the remnants of disrupted galaxies. These streams help us understand the Milky Way's formation. The galaxy's future includes continued star formation, interactions with satellites, and the eventual merger with Andromeda. It's a dynamic system. Observing the Milky Way requires multiple wavelengths. Visible light shows stars. Infrared reveals dust and cooler objects. Radio waves detect gas. X-rays highlight energetic regions. Telescopes like Hubble, Spitzer, and Gaia have mapped the galaxy. Gaia, in particular, measures the positions and motions of over 1 billion stars. It creates a 3D map of the Milky Way. Understanding the galaxy helps us understand our place in the universe. It provides context. It shows how stars and planets form. It reveals the processes that shape cosmic structures. The Milky Way is one of billions of galaxies, but it's special to us. It's where we live. It's where our story unfolds. Let's take one last look. The solar system, a tiny on the Orion arm nearby stars, scattered. The galactic center, distant and energetic. Spiral arms filled with stars and dust. This is our galaxy, our island in the cosmos, a place of motion, light, and mystery. We now zoom out from the Milky Way. Our home galaxy, vast and dynamic, is just one of many. It belongs to a collection of galaxies known as the local group, our immediate cosmic neighborhood. The local group contains more than 80 galaxies. Most are small dwarf galaxies. A few are large spirals. The dominant members are the Milky Way, Andromeda, and the Triangulum Galaxy. Andromeda, also known as M31, is the largest galaxy in the local group. It's a spiral galaxy located about 2.5 million light-years from Earth. It's similar in structure to the Milky Way, but slightly larger. Andromeda contains over 1 trillion stars. It has a prominent disk, spiral arms, and a central bulge. It also has a supermassive black hole at its center. Its outer regions are surrounded by satellite galaxies. The Milky Way and Andromeda are gravitationally bound. They're moving toward each other at about 110 kilometers per second. In roughly 4 billion years, they will collide and merge. This future collision will not be a violent crash. Stars are spaced far apart. Most will pass by each other, but gas and dust will interact, triggering new star formation. The result will be a new, larger galaxy, likely elliptical in shape. The Triangulum Galaxy, or M33, is the third largest member of the local group. It's a spiral galaxy located about 3 million light-years away. It's smaller than the Milky Way and Andromeda, but still significant. Triangulum is rich in star-forming regions. Its spiral arms contain bright nebulae and young stars. It may be gravitationally bound to Andromeda and could play a role in the future merger. The rest of the local group consists of dwarf galaxies. These include the Large and Small Magellanic Clouds, which orbit the Milky Way. They're irregular in shape and contain active star-forming regions. Other dwarf galaxies include Leo I, Leo II, Fornax, Sculptor, and Draco. These galaxies are faint, low in mass, and often dominated by dark matter. They orbit larger galaxies and are remnants of early cosmic structures. The local group spans about 10 million light-years. It's held together by gravity. Galaxies within it move relative to each other, influenced by mass and momentum. Beyond the local group lies a larger structure, the Virgo supercluster. This is a massive collection of galaxy groups and clusters, extending over 110 million light-years. The Virgo supercluster contains thousands of galaxies. It's centered around the Virgo cluster, a dense region of over 1,000 galaxies located about 55 million light-years from Earth. The Virgo cluster is rich in elliptical and spiral galaxies. It's a region of intense gravitational interactions. Galaxies collide, merge, and evolve. It's a dynamic environment. Our local group is located on the outskirts of the Virgo supercluster. We're part of a filament, a thread-like structure of galaxies and dark matter. These filaments connect clusters and groups across the universe. The Virgo supercluster is not isolated. It's part of an even larger structure, Laniakea. This supercluster redefines our understanding of cosmic geography. Laniakea, meaning immense heaven in Hawaiian, was identified in 2014. It includes a Virgo supercluster, the local group, and many other clusters. It spans over 500 million light years. Laniakea contains about 100,000 galaxies. It's shaped by gravity and cosmic flows. Galaxies move along filaments toward regions of higher density. These flows define the boundaries of superclusters. At the center of Laniakea is the Great Attractor, a gravitational anomaly that pulls galaxies toward it. Its exact nature is unclear. It may be a dense region of galaxies and dark matter. The Great Attractor influences the motion of the Milky Way and other galaxies. We're moving toward it at hundreds of kilometers per second. It's a reminder that gravity shapes the universe on all scales. Mapping these structures requires precise measurements. Redshift data reveals distance and motion. Surveys like the Sloan Digital Sky Survey and 2MASS chart the positions of galaxies. Cosmic flows show how galaxies move relative to each other. These flows trace the gravitational landscape of the universe. They reveal the structure of superclusters and voids. Voids are vast regions with few galaxies. They're the opposite of clusters. They span tens to hundreds of millions of light years. They help define the cosmic web. The cosmic web is the large-scale structure of the universe. It consists of filaments, clusters, and voids. Galaxies are not randomly distributed. They follow patterns shaped by gravity and dark matter. Dark matter plays a crucial role in these structures. It doesn't emit light, but it provides a mass needed to form clusters and filaments. It's the scaffolding of the universe. The Virgo supercluster and Laniakea are part of this web. They're nodes in a vast network. They connect to other superclusters like Hydra Centaurus and Perseus Pisces. These superclusters form walls and sheets. Between them lie voids. The result is a foam-like structure, dense region surrounded by emptiness. Understanding this structure helps us understand cosmic evolution. It shows how matter clumped together after the Big Bang. It reveals the influence of gravity, expansion, and dark energy. Dark energy is a mysterious force driving the accelerated expansion of the universe. It opposes gravity. It affects the motion of galaxies on large scales. The discovery of dark energy reshaped cosmology. It suggests the universe will continue expanding. Superclusters may drift apart. The cosmic web may stretch and thin. But for now, structures like the Virgo supercluster remain bound. Gravity holds them together. Galaxies orbit within them. Clusters interact. Stars form and die. Our place in this structure is humble. The Milky Way is one galaxy among billions. The local group is one group among thousands. Laniakea is one supercluster in a vast universe. Yet we can map it, we can measure it, we can understand it. Our instruments reach across millions of light years. Our models simulate cosmic evolution. We've come a long way from Earth, from the moon to the sun, from planets to stars, from the Milky Way to superclusters. Each step reveals more scale, more structure, more mystery. Let's take one last look. The Milky Way, a spiral galaxy. The local group, a small collection. The Virgo supercluster, a dense region. Laniakea, an immense heaven. This is our cosmic neighborhood, a region of galaxies' gravity and motion. We now explore one of the most profound structures in the known universe, the Laniakea supercluster. It's not just a collection of galaxies. It's a gravitational domain, a region where cosmic flows converge, a place shaped by invisible forces. Laniakea spans over 500 million light years. It contains around 100,000 galaxies. Its name means immense heaven in Hawaiian, a fitting description for a structure of such scale. This supercluster redefined how we map the universe. Before Laniakea, we identified superclusters based on proximity. But Laniakea is defined by motion, by the flow of galaxies toward a common gravitational center. That center is known as the Great Attractor. It's a gravitational anomaly located roughly 150 to 250 million light years from Earth. It pulls galaxies toward it, including the Milky Way, at speeds exceeding 600 kilometers per second. The Great Attractor is not a single object. It's a region of space with a high concentration of mass. It may include galaxy clusters, dark matter, and other dense structures. Its exact composition remains uncertain. One reason it's difficult to study is its location. It lies behind the zone of avoidance, a region obscured by the plane of the Milky Way. Dust and stars block our view. Observations are challenging. Despite this, surveys using X-ray and infrared telescopes have revealed clusters like Norma, Hydra, and Centaurus in the vicinity of the Great Attractor. These clusters may contribute to its gravitational pull. The Norma cluster, in particular, is massive. It contains thousands of galaxies and may be a key component of the Great Attractor. Its gravitational influence extends across vast distances. Galaxies within Laniakea move along cosmic flows. These flows are like rivers of galaxies, drawn toward regions of higher density. They define the boundaries of superclusters. The Milky Way, Andromeda, and other members of the local group are part of one such flow. We're moving toward the Great Attractor, carried by gravity across millions of light years. Mapping these flows requires precise measurements. Astronomers use redshift data, velocity surveys, and gravitational models. The Cosmic Flows Project was instrumental in defining Laniakea. Cosmic Flows tracks the motion of galaxies relative to the cosmic microwave background, the afterglow of the Big Bang. These motions reveal gravitational influences and large-scale structure. Laniakea is not isolated. It borders other superclusters, including Perseus Pisces, Coma, and Shapley. These regions also contain thousands of galaxies and exert gravitational forces. The Shapley supercluster, located beyond the Great Attractor, may be even more massive. It could be influencing the motion of the Great Attractor itself. The gravitational landscape is complex. These structures form part of the cosmic web, the large-scale pattern of matter in the universe. Filaments connect clusters. Voids separate them. Gravity shapes everything. Dark matter plays a central role. It doesn't emit light, but provides the mass needed to form and sustain superclusters. It binds galaxies together. It defines flows. Dark energy, on the other hand, drives expansion. It opposes gravity. It causes the universe to accelerate. Over time, it may stretch the cosmic web and isolate superclusters. For now, gravity dominates within Laniakea. Galaxies orbit, clusters interact, and flows converge. It's a dynamic region, rich in structure and motion. The scale is staggering. A single galaxy contains billions of stars. A cluster contains thousands of galaxies. A supercluster spans hundreds of millions of light years. And yet we can map it. We can measure it. We can understand it. Our instruments reach across space. Our models simulate evolution. Our data reveals hidden architecture. The discovery of Laniakea changed our perspective. It showed that our galaxy is part of a much larger system. It placed us within a gravitational context. It expanded our cosmic address. We're not just in the Milky Way. We're in the local group, in the Virgo supercluster, in Laniakea, moving toward the Great Attractor, part of a vast, interconnected web. This perspective is humbling. It shows how small we are, how vast the universe is, how gravity links everything, from stars to galaxies to superclusters. It also raises questions. What lies beyond Laniakea? Are there larger structures? Is the Great Attractor part of something even more massive? What is the ultimate shape of the universe? Some theories suggest the existence of cosmic walls, immense sheets of galaxies spanning billions of light years. Others propose multiverses, regions beyond our observable universe. But for now, we focus on what we can observe. Laniakea is the largest structure we're gravitationally bound to. It's our cosmic continent, our immense heaven. Let's take one last look. The Milky Way, drifting in the local group. The Virgo supercluster, surrounding us. Laniakea, stretching across space. The great attractor pulling us forward. This is gravity's architecture, a structure of motion, mass, and mystery. We now reach the outermost boundary of our journey, the edge of the observable universe. It's the farthest distance light has traveled to reach us since the beginning of time. Beyond this limit, we cannot see, not because nothing exists, but because light hasn't had time to arrive. The observable universe spans about 93 billion light-years in diameter. This number is larger than the universe's age, 13.8 billion years. Because space itself has expanded, light from distant galaxies has been stretched by cosmic expansion, increasing the distance between objects. We define the observable universe by the cosmic horizon, the limit of what we can detect. It's not a physical edge. It's a boundary of visibility. Beyond it, galaxies may exist, but their light hasn't reached us. Within this sphere, there are estimated to be over 2 trillion galaxies. Each galaxy contains billions of stars. Each star may host planets. The scale is incomprehensible. The light from the most distant galaxies we observe began its journey billions of years ago. We see them not as they are now, but as they were in the distant past. Observing the universe is like looking back in time. The cosmic microwave background marks the earliest light we can detect. It's the afterglow of the Big Bang, emitted about 380,000 years after the universe began. It's uniform, faint, and stretched across the sky. This radiation provides a snapshot of the early universe. It reveals density fluctuations, tiny variations that grew into galaxies and clusters. It's a cornerstone of cosmology. Beyond the cosmic microwave background lies the cosmic dark ages, a time before stars formed. We cannot observe this era directly. It's hidden from view, but models and simulations help us understand it. Eventually, the first stars ignited, galaxies formed, light began to travel, the universe became transparent, structures emerged, the cosmic web took shape. Today, we observe galaxies at various distances. Some are nearby, some are billions of light years away. Their light is redshifted, stretched by expansion. Redshift is a key tool in measuring distance. The Hubble Space Telescope and James Webb Space Telescope have revealed galaxies from the early universe. These galaxies are small, irregular, and rapidly forming stars. They show us how structure evolved. Quasars, extremely luminous active galactic nuclei, are among the brightest objects in the universe. They're powered by supermassive black holes. Some are visible from billions of light years away. Gamma-ray bursts, supernovae, and gravitational waves also provide information about distant events. Each signal adds to our understanding of the cosmos. The observable universe contains a vast range of structures: galaxies, clusters, superclusters, filaments, and voids. These structures form the cosmic web, shaped by gravity and dark matter. Dark matter makes up about 27% of the universe's mass energy content. It doesn't emit light, but it influences motion and structure. Its nature remains unknown. Dark energy accounts for about 68%. It drives the accelerated expansion of the universe. It's uniform, pervasive, and mysterious. It affects the fate of the cosmos. Ordinary matter, the atoms that make up stars, planets, and people, comprises only about 5%. We are a small part of the universe's composition. The expansion of the universe is accelerating. Galaxies are moving away from each other. Over time, distant galaxies will fade from view. The observable universe will shrink. Eventually, only nearby galaxies will remain visible. The cosmic horizon will contract. The universe will become darker, colder, and more isolated. This future is shaped by dark energy. If it remains constant, expansion will continue. If it increases, the universe may tear apart. If it decreases, gravity may slow expansion. These scenarios are theoretical. Observations continue. Models evolve. The fate of the universe is still uncertain. Some theories propose a cyclic universe, one that expands and contracts. Others suggest a multiverse, a collection of universes with different properties. These ideas are speculative but intriguing. The observable universe is not the whole universe. It's just the part we can see. Beyond it, space may continue indefinitely. Other regions may exist, other galaxies, other laws of physics. We may never observe these regions. Light from them may never reach us. They lie beyond our horizon, beyond our instruments, beyond our reach. But even within the observable universe, the scale is staggering. Trillions of galaxies, quadrillions of stars, uncountable planets, endless possibilities, and among them one small planet, orbiting one average star, in one spiral galaxy, in one supercluster, in one immense heaven, Earth. From here, we've looked outward, from the moon to the sun, from planets to stars, from the Milky Way to Laniakea, from the Great Attractor to the edge of visibility. Each step revealed more distance, more structure, more mystery. Each step expanded our perspective. We are small, but we are curious. We measure. We explore. We understand. We ask questions. We seek answers. The universe is vast, but it's knowable. It's observable. It's beautiful. Let's take one final look. The moon, our first step. The sun, our source. The planets, our companions. The stars, our neighbors. The galaxy, our home. The supercluster, our region. The observable universe, our horizon. And beyond, the unknown. This is the end of our journey, but not the end of wonder. Thank you for traveling with us. Sleep well and dream of stars.